Welcome to the video lecture on electric circuit analysis. In this video, we are going to see what is Norton's theorem and how to apply Norton's theorem for electric circuits. Norton's theorem states that a linear two-terminal complex circuit with two terminals AB can be replaced with an equivalent circuit consisting of a current source in parallel with the resistance Rn. This current source is called as Norton current or short circuit current, and this resistance Rn in parallel with the current source is called as Norton's resistance or Thevenin's resistance. So how to calculate this Norton's current or short circuit current? Short circuit these two terminals, find out the current flowing through the shorted terminal, and that current is what we call it as Norton current or short circuit current. How to find out Rn or RTH? It is a very similar procedure what we followed in Thevenin's resistance. You have to look from this side. While doing that, you have to look from this side and calculate the equivalent resistance of this entire network. While doing that, I have to turn off all the independent sources. Meaning is, if there is any current source available in the circuit, you have to open circuit it. So open circuit the current source. And I have to short circuit all the independent voltage sources. Only independent voltage sources. Dependent sources, you should not disturb the dependent sources. You have to leave in the circuit as it is. So there are two steps involved in Norton's theorem. First step is I want to calculate the Norton's resistance, and the second step is I want to calculate the Norton's current. So now let us try to apply the statement of Norton's theorem to few circuits and understand how Norton theorem works. So now this is the circuit given. I want to calculate or I want to find out the Norton's equivalent circuit for the figure shown across the terminals AB. So here I have two sources, two independent sources. One is a current source, other one is the voltage source. So as I already told you that there are two steps involved. One is, first step I want to calculate Norton's resistance, and second step I want to calculate Norton's current. To calculate Norton's resistance, I want to turn off all the independent sources, which means that I have to open circuit the current source and short circuit the voltage source. So open circuiting, I am going to remove this branch completely. I am going to remove this. Short circuiting, I am going to remove this voltage source and put a short like this. So once I do that, I get an equivalent circuit, which is something like what I am shown here. To calculate the Norton's resistance, I have to look from this side of the circuit. So when I look from this side of the circuit, 8 ohm, 4 ohm and 8 ohm are in series, and this series combination is in parallel with 5. So the equivalent circuit will look something like what I am trying to draw here. I have two resistances in parallel phi. One is this terminal A and this is terminal B. This is 5 ohm resistance, which is what it is given here, and this resistance is an equivalent of this 8 plus 4 plus 8. So this is 8 plus 4 plus 8, which is equal to 20 ohms. So the equivalent circuit when looking at this side is what I call it as Norton's equivalent. So which is given by Rn is equals to 20 and 5 are in parallel. So 20 into 5 divided by 20 plus 5, which gives me 100 divided by 25. 100 divided by 25 gives me Rn is equals to 4 ohms. So this is the Thevenin's equivalent resistance or Norton's equivalent resistance. The procedure for calculating Norton's equivalent resistance and Thevenin's equivalent resistance are same. So first step is completed. In the second step, I want to calculate the Norton's current. To calculate Norton's current, I have to short this terminal. Once I short it, I want to find out or calculate what is the current flowing through this shorted terminal, and that current is what I call it as Norton's current. I have to keep all my sources similar. I should not disturb my sources. It has to be taken into account while calculating the Norton's current. So I short it. The equivalent circuit will become something like this. Equivalent circuit will become something like this. So when I look at, once I short, the resistance here will be equal to 0. So when the resistance is equal to 0, if there is any parallel resistance available, that resistance also will be equal to 0. Say for example, here in this case, look from this side. I am just drawing only the other side. I mean this side of the circuit alone. So it has a 5 ohm resistor, in parallel with a short. So this is 5 ohm and this is resistance is having 0 ohms here. So it is shorted. So when I calculate the equivalent resistance here, 5 into 0 is 0 by 5 plus 0 is 0. So the equivalent resistance is again 0. So once the equivalent resistance is 0, which means that it is going to be a direct short. So this resistance 5 ohm does not come into picture at all. So I can remove this resistance. So I will remove this resistance and draw the circuit again for easy understanding. So it will look something like what I am trying to draw here. I will have a current source and I have a resistance and a voltage source. So let me try to draw that. I have a resistance and a voltage source, which is something like what I am trying to draw here. Then I have 8 ohm and 8 ohm. So this I am trying to draw. This is 8 ohm and this is another 8 ohm. And since this 5 ohm and this R and the shorted terminal is totally short, as I explained earlier, I can put a direct short here, because this 5 ohm resistance is becoming 0 by combining with the parallel short. So this 5 ohm does not come into picture. So let me try to write this: 8 ohm, 4 ohm, 12 volt and 2 amperes. So now I want to calculate the current through this particular shorted terminal, which I call it as IN. So to find out the current through this, let me apply the simple Kirchhoff's voltage law here. I mean mesh analysis. There is a current here which flows, which I call it as I1, and there is another current which flows here, which I call it as I2. Now I2 is nothing but IN. So I can, if I calculate I2, then which is equal to the Norton's current IN, because in this branch only I2 and IN flows, both are in the same direction. So I2 is equal to IN. So let me name all these points A. But when you look at this point, I1 is equal to 2 amperes. So if you look at this current in this branch, I1 is equal to 2 amperes. So let me name all this: A, B, C, D, E, F, and this I keep it as F dash. So by looking into the branch FA, I1 is equal to 2 amperes. I1 is equal to 2 amperes. Now I want to write the mesh equation for this loop, which is B, C, D, E, F dash, B loop, and the current in it is I2, which is the primary current. So let me try to write the mesh equation. Branch, either it is a potential dropping element or potential rising element. Let me first take the BC branch. So BC branch, I am moving from B to C. Current is also moving in the same direction. Look at this current I2. I2 is flowing from B to C. So this is a potential drop. So 8 I2 is a potential drop and there is no potential rise. And C to D, no element present. So I leave it. D to E, D to E, again D to E, current also flows from D to E. So I am also moving from D to E, current is also flowing from D to E. So it is again 8 I2, again it is potential drop. Then E to F dash, look at the current I2 is flowing from minus to plus, so it is a potential rise. So 12 volt is a potential rise. And F dash to B, there are two currents, F dash to B, I2 flows, B to F dash, I1 flows. So 4 I2 is potential drop and 4 I1 is potential rise. So as of Kirchhoff's voltage law is concerned, sum of potential drop is equal to sum of potential rise. So 8 plus 8, 16 plus 4, 20 I2 is equal to 12 plus 4 I1. 12 plus 4 I1. I1 already we have calculated. Let me have this as equation 1 and this as equation 2. Substitute 1 in 2, we get 20 I2 equal to 12 plus 4 into I1 is 2. So this becomes 12 plus 8. So 20 I2 equal to 20 I2 equal to 20. So I2 equal to 1 amperes. As already told that I2 is nothing but IN, because in this CD branch I2 also flows from C to D, IN is also flowing from C to D. Therefore IN Norton current is equal to I2, which is equal to 1 ampere. So the equivalent circuit of the given network will be having a Norton's resistance of 4 ohm and Norton's current of 1 ampere, and the circuit will look something like this. So I will have a Norton current of 1 ampere and a Norton resistance of 4 ohms. This is the terminal AB. Norton's resistance is 4 ohm, so this is a 4 ohm. So this is the equivalent circuit, Norton's equivalent circuit for the circuit shown in the figure. This is problem 1. Now let us go for the next problem. I want to find out the Norton's equivalent circuit for the figure shown in the figure at terminals AB. As I told already that again we have two steps in it. First step is I want to calculate the Norton's resistance. To calculate Norton's resistance, I have to short circuit this voltage source and open circuit this current source. So when I do that, the equivalent circuit will be something like this. I short this, open that, open the current source. So I will get A, B, this is 6 ohm, this is 3 ohm and this is another 3 ohm. These points I just opened, so it is left empty. So now these two are in series, totally 6 ohm, and this series combination is in parallel with this. So when I look from this side, this is in parallel with this two resistances in series. So Rn is equals to 6 into 6 divided by 6 plus 6, which is 36 by 12, which is equal to 3 ohms. So Norton's resistance for the given problem is 3 ohms. How to calculate the Norton's current? I want to short this and I want to calculate what is the current flowing through this resistance, through the shorted terminals. So for which I should consider all the sources. So once I try to consider all the sources, I will remove this. So I'm going to consider all the sources now. So the current which is flowing here, I can easily do by converting this into an equivalent current source. So when I try to convert this into an equivalent current source, I will get a current source heading up 15 by 3, which is 5 amps. 5 amps current will be flowing, and that will be in parallel with a 3 ohm resistor, and that will be in parallel with a 4 amps current. This part 4 amps, this is 3 ohms, and that will be in series with 3 ohm and in series with 6 ohm, and this current IN. This is terminal A and this is terminal B. Now if I look at very clearly, this portion is having a short and a resistance. A short and a resistance is equivalent to a short. So again I can replace this complete thing with a short completely. So the equivalent circuit will become something like this. So this is 5 amps and 3 ohms, a 4 amps. So this is shorted. So this is 3 ohms and this is what I call it as IN. Now this point, entire point is the same point, so which is nothing wrong. I can redraw this network something like what I am going to show here. So this is 5 amps, a 3 ohm, a 4 ampere current source, and the 3 ohm, something like this, 3 ohm. The current through 3 ohm is nothing but the Norton current, so I can mark IN here. Now if you look at, I can add these two, both are heading up. So this is 4 amps and this is 5 amps, so totally 9 amps current is going to flow. 9 amps current is going to flow, and there are two 3 ohm resistance, 3 ohms, the first 3 ohm and the next 3 ohm, and the current through this is IN. So now how to calculate IN? You can apply current division rule. IN is equal to total current into opposite branch resistance, this is 3, opposite branch resistance divided by sum of the resistances. So this becomes again 4.5 amperes. So IN is 4.5 amperes. IN is 4.5 amperes and RN is 3 ohms. RN is 3 ohms. So the equivalent circuit will look something like this: 4.5 amperes and parallel with resistance, which is what we call it as the Norton's resistance or Thevenin's resistance, which is of 3 ohms in the problem. So this is the equivalent circuit for the given electrical network, Norton's equivalent circuit for the given electrical network. Now let us go for the next problem. This problem is little different, where I have a dependent source. Independent source, as I told you, can turn off, but dependent source I cannot turn off as it is. So there is a small confusion here to understand. So now let us try to find out how to solve this problem. So first step again, Rn I want to calculate. To calculate Rn, since it is a dependent source, to calculate Rn, I assume that there is a dependent source available. To calculate Rn, I assume that I inject a voltage of 1 volt across these terminals, as shown in the figure, something like this, voltage of 1 volt, and I calculate this I naught. I calculate this I naught, and this is done by shorting this independent source. If there is any independent source available, I will short it, voltage source. If there is any independent current source available, I will open circuit it. After doing that, there is a dependent source still available. So to calculate the Rn, what we do, we apply a voltage of 1 volt at this AB terminal and calculate this I naught. Now, after calculating this I naught, Rn is equal to V naught by I naught. V naught by I naught, which is V naught is 1 volt because we are applying it, and I naught I calculate. I use this calculated value to calculate this Rn. Now I want to find out this I naught. How to calculate this I naught? Now look at this. Again, this is a short, so the resistance here will be equal to 0. So if this is a short and the resistance is equal to 0, all the current will be flowing through this path only, because it is the short circuit path. There will not be any current flowing through this 4 ohm resistor, because resistance is lesser, higher the current. Resistance is nothing but it opposes the flow of current. So if higher the resistance, lesser the current. If lesser the resistance, higher the current. So since the current is, resistance is 0, current will be enormous. So there will not be any flow of current through this branch. So Ix is naturally 0. So because all the current flows through this shorted path, there will not be any current flowing through this 4 ohm resistance. So Ix will be equal to 0. If Ix is equal to 0, this also will become 0. So the equivalent circuit will become something like what I am trying to draw here. So this is plus minus 1 volt and 5 ohms. This is how the equivalent circuit looks like. Now how to calculate the current I naught? I naught is equal to simply V equal to IR. So I equal to V by R. V we know it. It is 1. I is 5. Sorry, R is 5. So I naught is 1 by 5. Use this here. So this becomes 1 divided by 1 by 5, which means that Rn equal to 5 ohms. Rn equal to 5 ohms. That is Norton's current. So first step is completed. To find out the second step, let us go here. What is that we do? We just short circuit this AB terminal and try to find out what is the current flowing here. To do this, we can apply a simple principle, which Ix is the current which is flowing through this 4 ohm resistor, which is just parallel with this 10 volt source. So current Ix is equal to 10 by 4 V by R. So this is equal to 2.5 amperes. Similarly, the current which is flowing this point and this point both are equal because it is a complete short. So this 5 ohm is also in parallel with 10 volt. So current through this 5 ohm resistor is I 5 ohm is equals to 10 by 5, which is equal to 2 amps. So here 2 amps, and this current which is coming out is 2.5 amps, and this becomes 2 into 2.5 is 5. So 5 plus 2, this 5 comes here, this 5 comes here, this 2 comes here. So 5 plus 2 is 7 amperes. So IN is equal to 7 amperes. So the equivalent circuit is Rn is 5 ohms and In is equals to 7 amperes. So the equivalent circuit will become something like 7 amperes and a parallel resistance which is equal to 5 ohms. So this is how the Norton's equivalent circuit can be obtained for any given electrical two-terminal linear networks. Thank you for your patient listening. Hope you enjoyed this video. Thank you.